Hi, I'm Maitreya. I am a PhD student at Arizona State University. I'm working with Dr. Yang and Dr. Baral. And today I will be discussing about what are the challenges associated with the resources requirements for text-to-image generative models. So let's first take a quick look at what kind of T2I generative models are we talking about. So we all know that diffusion related T2I models are getting more and more popular these days because of their efficiency in generating the better quality images, and at the same time ability to follow the very complex prompts such as like a photo of white small furry dog. But if you look at more closely, there are two types of different methodology for these T2I models. First one is the Changuner introduced, which is latent diffusion models. So in latent diffusion models, we have a single model, which is diffusion generator, which accepts the text embeddings through cross-attention layers and generates the image corresponding to that text. At the same time, we have another family of models, which is called Unclip, also known as DALI 2. And this model takes a slightly bit of a different approach, which introduces one additional module, which is called the, just a second. Yeah, so one additional module, which is text to image prior. So this text to image prior first maps the input text embedding to the image embeddings. And that this estimated image embedding is used to condition the diffusion models. So we all know that all of these models requires a diffusion process, and there are many limitations associated with when it comes to the resources. But before we talk about that, let's look at what kind of evaluations are important for these models. So not only photorealistic matters, but how much these models follow the text also is quite important. And there are many benchmarks that focuses on these different compositions, such as color composition, like a blue horse and a brown vase. And we can see that the model is not understanding the brown vase at all. And there are many other composition categories like shape composition, texture composition, and the spatial composition. So throughout this whole talk, when I measure the performance, I will be measuring average performance over all these compositions. And then we will talk about like how parameter efficiency or resource efficiency can play a big role in these settings. So if we simply put the performance chart for all these different state-of-the-art models, such as Stable Diffusion or any Unclip series model, and this the talk is before DALI 3 came out. So DALI 3 is exceptionally performing really well for same compositions. But if we ignore the DALI 3, then we can still see that the Stable Diffusion XL and the DALI 2 are open source or private like respective state-of-the-art models. So now let's talk about the resource requirements. And when we say resource requirements, like we want to discuss how much time does it take to train a model from scratch. So what contributes to this increasing resource requirements? We know very well that nowadays model parameters are becoming more and more important. We need to feed more and more high quality data set. Image resolution also plays into a picture. And sometimes we inefficiently train our models, and that also contributes to increasing resource requirements. So in previous model, in previous chart, let's add one more dimensionality, which is the parameters. And then we can see that the Stable Diffusion version 1 and 2 are much less in the parameters, but they are also performing very poorly. And we find a same trend, like if you keep increasing the parameters, then you are achieving more better and better results for like in terms of compositions. So there is another dimension apart from parameter, which is the data size. So how much data are we using to train this model? If you are using too much data set, that also means that we want to train this model for long period of time. So for instance, if you look at Stable Diffusion series, whether it's version 2, 1 or XL, they use a lot of data set, like 400 million to up to 2 billion image text pairs. And while if you look at the some of the open source Unclip implementations or the original DALI 2 paper, they are trained on much less data set, but they're still able to outperform models that are trained on big data sets. So overall, we find that two interesting insights. That amount of data seems to matter less, but we still require hundreds of millions of image text pairs to train these models. And another part is, if we look at closer look, all of these models are at least of 2 billion parameters. And nowadays, like we are getting DALI 3, which is like 7 billion parameters, Kandinsky version 3, which is also 7 to 8 billion parameters. So it seems that these resources are demand of resources are increasing day by day. So how can we improve this text to image mapping without requiring a lot of resources? So to take a step towards in this direction, I will be next talking about our recent work Eclipse, where we try to propose a resource efficient text to image prior for these T2I models. So before initially, like I introduced, there are two types of model families, like the LDM and the unclip. And previous benchmark, we showed that the unclip model are more and more like data efficient. And because they are having this text to image prior, which is external to the diffusion generator. So we have two different models, and both model contributes to one model solely contributes to text to image mapping, and other model just generates the image from a single embedding vector. So in this work, we focus on how we can improve this text to image priors and in terms of resource efficiency, and while still maintain the performance of these state of the art big models. And throughout these experiments, we take the open source trained unclip models such as Carlo and Kandinsky, and we are really grateful for the community to provide this model open source. Okay, so what are the text to image priors? So text to image priors are same as any other T2I LDM related models, but at very smaller scale. So instead of having generating a pixel values or even latent space, WACV' latent space, here we are just trying to estimate a single embedding vector, let's say 1280 dimension or 768 dimension from a given text embedding. And also, this original method was proposed by the OpenAI authors, and they also proposed diffusion prior as an modeling strategy. But this diffusion prior is slightly different than the diffusion loss we are using in a day-to-day basis. So typically, we estimate the normal Gaussian noise. But in this case, for the prior, authors propose to directly estimate the original vision embedding instead of estimating the noise. I will come to that how I will come to the next slides, like how this simple change in the modeling strategy can impact into the resource requirements. So if you look at this prior itself is 1 billion parameter. Even though we are just doing embedding to embedding mapping, it still requires a lot of parameters to achieve this performance. Plus, we want to train this model as in diffusion models, and that further adds to the amount of resource requirements due to slower conversions. So we did a couple of the empirical studies that whether do we really need these diffusion steps for the prior models, because at the end we look at that at irrespective of the time steps, model is only estimating the final ground truth image embedding. So why not we just use the single step or two step? Why do we want to go for 25 or even 50 steps? So we observed that if you keep increasing the prior steps, surprisingly model performance decreases. And compared to when the prior step is equal to 2. And we performed these experiments on lots of MS COCO and even composition benchmark data set. And this human preferences is modeled by the PIC score model. So similarly, why this is happening? Like what's causing the prior model to decrease the performance with increasing time steps? So if you look at the standard DDPM inference time scheduler, we see that we are adding this additional noise term after each inference step, except for the last step. And this noise term may or may not be observed during the training stage, because at the end, we just trying to estimate the ground truth embeddings. And if we do the experiment that we slowly increase the like this amount of noise added, and we find that if you keep increasing the noise, again, model performance drops. So, and that is explainable because during the training, we are not training this model to estimate the like fine noise, estimate the Gaussian noise, but we are just trying to estimate the final embeddings. So at the end, we removed this noise parameter and we improved the like decrease the prior steps to 2. And we found that all these open source unclip models performs much better than the original like diffusion priors. Okay, so now we got this interesting insight. So what if we just remove the diffusion modeling, right? What if we just have simple non-linear projection layers to do this text to image mapping? So if you look at more carefully that this projection loss, which is essentially just takes the text embedding as an input and estimates the vision embedding, which is a special case of the diffusion prior loss when the T equal to capital T throughout the whole training stage. Okay, but if we go from diffusion loss to the projection loss, we observe that we lose the ability to perform the classifier free guidance. And this classifier free guidance is really, really important to achieve the generalization. Let's say our model is trained on red apples and the black grapes. Can it generalize during inference time, like for black apples? So this classifier free guidance contributes a lot towards this generalization. So if we compare both these approaches side by side, then diffusion models are slower in convergence, require more parameter, but are better at generalization. While the projection priors are faster in convergence, are parameter efficient, but cannot generalize outside the data set, because in projection loss, we are directly maximizing the evidence lower bound on the training data set. So if we do not cover sufficient amount of distribution, the model cannot generalize on the OOD scenarios. So how can we improve this? Like how can we improve this projection layer and enjoy the benefits of both of these approaches? So this text-to-image generative models took an inspiration heavily initially from the pre-trained vision language model. So if you look at the stable diffusion or the initial versions of stable diffusion or unclip models, they heavily rely on the pre-trained clip models. So what pre-trained clip models are? So we are training text encoders and image encoders in a way that both of the embeddings are semantically aligned, and we can measure the semantic alignment using the cosine similarity. However, if we take a look at the existing modeling strategies, we are not effectively utilizing the semantic alignment property. We are just what we are trying to do is just map one text embedding to corresponding image embedding, which is just one-to-one mapping. And because of that, we are heavily relying on the parameters to overcome this limitation in our training strategies. So if we take a high level overview, like how standard unclip priors are being calculated, here we can see that it's the same modeling strategy. Priors are defined as it is, whether it's diffusion priors or it's a projection based priors. So what we are doing is we are just feeding the like one-on-one mapping, like orange circle to orange circle image, like, and blue circle text to blue circle image. And because of that, some OOD scenarios are not efficiently learned by this model. To overcome this problem, we want to utilize the semantic alignment property. And what's the best way to use it other than the contrastive loss? Because this clip model is also trained on the contrastive loss. So what we want to do is, so let's say we have estimated vision embedding from a corresponding positive text embedding. So we want to maximize the similarity between these two embeddings, and we want to minimize the similarity between the negative pairs. So overall, if you look at the objective looks like this. So we have standard projection objective, because even though clip model are trained on the like such a way that we want to align the semantic space, both like modalities can have different distribution itself. So as we still need the traditional projection loss, And also we add the additional partial contrastive loss, which just focuses on the text to image prediction. Overall, we found that adding this contrastive objective along with the projection objective, we drastically improve the generalization of these models. So if you look at overall comparison, that eclipse priors are able to achieve faster conversation, more parameter efficient, and are able to generalize even better than the diffusion priors. Okay, so these were the overview. Let's talk about the numbers, like how good eclipse priors are getting. So if we take a quick look, then in just terms of an prior model, which is just one module of the whole T2I models, we compress this model by about 97%. So instead of training a 1 billion parameter model, you can just train 33 million parameter prior model, and you can still achieve the state-of-the-art performance. Similarly, if we just use this prior model with the existing pipeline, let's say Carlo or Kandinsky models, we can still see the overall compression of the 47 to 48%. And we still observe the better performance of in terms of compositionality. Apart from parameters, we need to consider the training data efficiency. So Eclipse, because of we are doing essentially knowledge distillation from the pre-trained vision language models, we don't require huge amount of data set to do this text to image mapping. And we can easily train our model with less than 10 million image text pairs. So if you look at compare the Carlo or Kandinsky open source prior models, they are trained on more than 101, about 115 and 175 million image text pairs. But while Eclipse priors are only trained on the less than 10 million image text pairs, and they can still maintain the performance. So how does improving the parameters and the data dependency improve the overall requirement of training this model from scratch? So if you look at stable diffusion was trained on 150,000 GPU hours, and that is a lot of and in typically standard academic labs, we cannot afford to host our training on AWS or any of these models, and we have to rely on these big labs to open source their models. And similarly, there is no standard numbers available for training the text to image prior. But one of the work from the Adobe actually released how much resources they actually use to train these priors. And we can still observe that even though we use text to image diffusion priors, they at least require 1,000 GPU hours, because their model size is at least 250 million parameters. And they also train it on the millions of image text pairs. Even though these priors are domain-specific priors, and if you look at the general text-to-image priors like Leon prior, they have not released the total number of computers, but they have trained 1 billion parameter, and they have trained about Leon 2B, if not 5B model. So compared to these settings, we find that Eclipse can be trained in less than a day, which is just 50 GPU hours. If you have 4 GPUs, that will be trained in less than 12 hours. So, and the model parameters are just merely 33 to 34 million parameters, and can easily be trained on the less than 10 million image text pairs. So how does it perform with respect to different compositions? And we find that this Eclipse prior, if not performing better than the state of the art, they still maintain the performance of this big prior model. So if you look at the comparison with Kandinsky or the Carlo, each of these Eclipse variants are compressing a lot of parameters. And even though they are trained on, let's say, only 0.6 million to 10 million image text pairs, they consistently outperform the respective baseline and achieve the performance that of the DALI 2. We further perform the experiments on the control setting, where we fix the model size to all baseline models, including projection, diffusion, Eclipse to 33 million. We fix the data, hyperparameter, and random seed, and we train all these models for longer period of time so that all baseline models have sufficient time to converge. And we find that Eclipse prior consistently outperforms all the other baseline, whether it's projection or the diffusion baseline. Whether it's a colored image generator, whether it's a condensed key image generator, we observe consistent performance of the Eclipse across these baselines. Now, if we put the Eclipse over our previous benchmarking strategy, so we find that Eclipse reduces the 72% of the parameters compared to DALI2 while maintaining the performance. And it improves the 55% in terms of an composition while maintaining the similar level of parameter requirements. So we further perform the human evaluations, and we find that the Eclipse still maintains the same level of quality compared to the this open source big models. And we also release the model weights and demo everything online for others to play with and contribute over this line of work. Similar to any other works, like there are certain limitations and a very promising future direction. So here we observed that pre-trained clip model can be efficiently used to improve the T2I models. So what if we use the better clip models, or we train the clip models in a better way, such as like LIT, Meru, or SIGLIP? These models have shown that by training these clip models more effectively, we can get better at compositionality and text-to-image alignment. So if we can incorporate this kind of clip models, we can directly observe this improvement of the T2I model. And the good part, we don't need to invest a lot of resources to get these improvements. Another still major component that we have not yet addressed in Eclipse is the diffusion image decoders. So if in Unclip stack, there are two different modules, prior and the diffusion image decoder. So we were able to improve the prior drastically, but there is still future work remains. Then how do we want to improve these decoders? And some of the works like diffusion image transformers are showing promising direction. And these works can be directly incorporated with the Eclipse because of the modularity of the Unclip stack. Similarly, in last couple of weeks, we have seen that the quality of the data matters a lot for these T2I models. And by improving this caption quality of the Leon dataset, we can directly improve the clip further. And that will immediately lead to the improvement of the T2I models without any resource investment. And thank you for having me for this tutorial. And this work would not have been possible without the excellent collaborators.